If the head decreases till the top half of the boundary becomes ineffective, the lower half will act as a weir, over which the water will flow with a fluid number that is no longer independently variable, but depends upon the geometry of the flow boundaries. If a weir is used for flow measurement, the lower as well as the upper surface of the nap must be kept at atmospheric pressure by ventilation. The rise in water level under the nap is now purely a dynamic effect involved in the deflection of the stream by the floor. If, however, the ventilation tube is removed, the air under the nap will gradually be carried away. As this occurs, the difference in pressure will cause the nap to be depressed in accordance with the flow net and Bernoulli equation. In passing, it might be noted that large spillways are built according to the profile of the undersurface of a ventilated nap, on the reasonable assumption that the resistance of the solid boundary will not appreciably change the distribution of velocity and pressure at the crest. Although the Froude number of the ventilated weir is fixed by the geometry, it can be reduced towards zero if the downstream side is gradually submerged by the tailwater. On the other hand, it can be increased far above unity if the flow is made to approach the weir with sufficient velocity to overshoot it, as is seen here at successively greater values of the Froude number. However, in the plot of the Euler number, or discharge coefficient, against the Froude number, which shows these two distinct zones of operation, there will be a gap between them, in which flow at the assumed depth will be physically impossible. In other words, as the Froude number is reduced toward unity, the approach section will abruptly become submerged by backwater. Further perspective in the matter is obtained by considering flow that is nearly enough uniform for the one-dimensional approximation to apply.